recorder is started already. I'm gonna get started with the class.
See, but it was easy. Yeah, like less than 10 minutes, right?
So how was the program? How was the homework assignment?
Good.
It's not bad, okay. So I'll give you the solution today, but I'll give you two solutions instead of one. The quick solution is the one that you guys worked on already, which is the successive subtraction method. So we'll go through that one first. You know, that one we probably can breeze through, you know, in a reasonably short amount of time. And then the other way is to use the actual way of doing division, but we'll do it in binary using the toy architecture, and you'll see how it is kind of tedious, but also, you know, it is going to be faster too. All right, so we'll go ahead and do it the easy way, or the way that we talked about already. So I'm going to give you the C code. Turn on the projector. Let's see. We've still got about 2 more months to go before the Christmas special of Doctor Who is going to be in theaters.
Is it new?
Huh?
Is it a new one, or is it like a rerun?
It's Christmas special, so it's new.
They do one every year, right?
Yep, there's a Christmas special every year. The one that I like the most is the one that has Santa Claus, the elves, and you go like, it's a science fiction show. You know, why would they have, you know, Santa Claus and Rudolph, you know, the elves and so on and so forth? It's really good. That one was one of my favorites. Yeah. So I'm waiting for that. 2 months. 2 months.
Pretty much exactly. Pretty much exactly 2 months.
Yep. I think it's going to be in theaters on the 27th in December. Yep. Cool. All right. So we'll go ahead and take a look at the homework assignment that was due this morning. A has, okay, so you know, A has the dividend, and then B has the divisor. All right, so the code to do it is actually pretty simple. You just say, you know, as long as the divisor, the dividend, is less than or equal to the divisor. Okay, so this has to be the other way around, greater than or equal to. So as long as the dividend is greater than or equal to the divisor, you know, stay in the loop. And before this, you might want to keep track of C, because C is going to be the quotient. Okay. So C, you know, has to be initialized to 0, but everything starts with 0 anyway when you reset the processor, so that's not explicitly needed. Okay. Inside the loop here, we have to increment C, which is our quotient for each iteration, and then we also have to subtract B from A, so that we have that much less for the next iteration. When it's all done, we don't have to do anything else, because C automatically has the quotient, and whatever is left in A is the remainder. All done. Okay. So now the question is, how do we turn this into assembly code using the toy processor? So what I'll do is I'm going to insert comments in front of every single line, and we'll tackle the easy ones first. Okay, so this one is easy because it's just increment C. This one is also easy because it's just subtraction AB. Because, you know, that's, you know, those are single instruction stuff. This one, if you really want to do it, you can do it with a LDIC with a 0. You can also do it with a sub CC. Subtracting C from C will also end up with the same thing. Sub CC is 1, faster, and 2, it only uses 1 byte instead of 2 bytes, because LDIC 0 would actually take up 2 bytes. So sub CC is better, except it modifies the flags. Okay, so if you're in a situation where you don't want to modify the flags, don't use, you know, sub. But in this case, it's okay, because, you know, I need to have a compare instruction at the beginning of the loop anyway. So this is the label for the beginning of the loop, and this is the label for the end of the loop, where there's a single halt instruction after, because we need to stop the program from executing any further. That also means, you know, at this point we have a JMPI, an unconditional branch, to go back to the beginning. because that's a loop. Otherwise, it just falls through and performs one iteration at the most, and it's done. All right, so this is the kind of the crucial part. The crucial part is, how do I make this loop so that when A is less than B, we go to end while end. So we need a compare instruction. So we compare AB in this case, and we say JCI to while end. JCI is the correct one instead of JSI or JLI because the numbers are unsigned. Now you might say, but I use JSI and it seemed to work. Well, it will only work if your dividend is less than 128. The moment your dividend hits 128, it won't work correctly anymore because 128 is 80 in hexadecimal, which is also 1 followed by 7 zeros. So the sign flag is on automatically, and well, it depends on what you're subtracting from it, because but it will definitely affect the result. So I would definitely test your program using test cases where the wrong J jump instruction would not work correctly. Okay, so I think that's it. That's the entire program as far as I can see. Does it look right to you guys? Seems right to me. Yeah. Okay, so we'll Control A, Control C, and then go to my folder, go to the assembler. Okay, I opened the assembler many times this month. Yes. Okay, so we go to the shared folder. Assembler is inside processor. There we go. And I also found a way to use this offline. I haven't tried it yet, but if you look up Google Documents offline, there are instructions. You can install an add-on to Chrome. Then you can actually run this spreadsheet offline, which I think can be kind of cool because that way you don't have to rely on being online. So it's all done. No syntax errors or no errors of any kind. We go to the RAM file. And then we say download as CSV, and we'll call this one divide. Okay, so now it's time to start up the virtual machine. Sim, generic, and then we go to the processor to start up the processor. Okay, and do a right click. Load image. There we go. And then we'll go ahead and change the registers before we start executing. Let's try a 9-1. Okay, set 9-1, 9-1, and we'll make this one 1-0. Okay, because that makes it pretty easy. The quotient is supposed to be 9 with a remainder of 1 in register A. Okay. This one will not work if people use the wrong jump instruction. If people use a JSI or JLI, this one won't work correctly. All right, let's give it a try. So we go back to main. Okay. So if you're feeling really confident, you can just kind of run it and test the registers and see whether they are correct or not. If you're not entirely confident that your program will work correctly, I strongly suggest that we use logging as a feature. So you basically want to log the program counter for sure, because this shows you where you are executing. You want to track down the registers, so you want to go to the register bank, track down register A, register B, and register C. You might want to track down flags as a register too, because after the compare or the subtraction, you want to kind of look at, okay, which flags are set or reset. So I would say minimally, these are the ones that you should track if you're debugging your program. So we close, and then we start clocking, which is Control K on the keyboard. Okay, it's all done. Control K again to stop the clock. Go to the register bank, and we got 9-1. So it's all done correctly. All right, so quick test. It's Obviously, it's not complete validation that this algorithm works for sure. So you have to kind of throw additional test cases at it. Like 0 divided by 5, okay, you should get 0, for both, okay, 0 as quotient and 0 for remainder. You might want to try 3 divided by 5 because you should get 0 for the quotient and 3 for the remainder, okay, so those are kind of like, tricky test cases. 255 divided by 1, you should get 255 as your quotient and 0 for your remainder. That sort of thing. Just kind of test all the boundary cases to make sure that your program works, for all the extreme cases. So, are there any questions about this particular algorithm, the successive subtraction method? Yep.
Not about the algorithm. I'm just curious. What does the JCI do?
JZI? I don't have a JZI. I don't need it.
Okay.
Because I'm looking for the negation of this condition to get out of the loop. The negation of A is greater than or equal to B is A is less than B. And it turns out that we have JCI to handle just that.
Okay.
On the other hand, if we are looking for A is less than or equal to B, then you can do a JCI and then a JZI. So this way it will branch whether it is less than or equal to. Okay. Are there any other questions about the successive division, method? No questions? All right. So with this out of the way, I'm going to show you the alternative version, which I don't think anyone is doing because it's a little bit more complicated and it certainly takes a little bit more effort to get it to work and to debug too. So we'll take a look at that one. I'm looking at my camera because it seems to have some keyhole distortion or keystone distortion. There we go. Let me go a little higher. Thing is twisted a little bit. Okay, so this is how we do division in base 10. Okay, I'm going to show you, just in general, a single example. So let's say we have 4,631 divided by 71. Okay, I'm just randomly picking some number. To do this actually correctly in a way that you can do it, with a computer, we're going to do it in a way that looks like this. So we look at 4 by itself and we ask, are there any 71 in 4? Well, the answer is pretty clear. There's no. Okay, so we put a 0 here. 0 times 71 is a 0. 4 minus 0 is a 4. And then we take a 6 down here and then we ask, is there a 71 in 46? At least one. The answer is no. Okay, put another 0 here. 0 times 71 is 0, 0. So we subtract 0, 0 from 46. We get 46 back. And then we put the 3 down here. And then we ask, how many 71s do we have in 463? The answer is about 6, I would say. So 6 times 71 is 6 here, 42 here. And then we subtract these two numbers. So this number, 426, is 6, which is a single digit in the quotient, times the divisor. So 6 times 71 is this number, so we do the subtraction. This is 7 with a borrow. This is a 3 here. And then we take this one from the dividend. 371, looks like we got about 5 of these, okay? So we got a 5 here and a 35 here. We do the subtraction. We get a 6 and a 1 here. So the answer is 65 with a remainder of 16. This is the way we do subtraction, right? I mean, this is not successive subtraction, because to do the successive subtraction, we'll be subtracting 71 65 times, which is going to take a lot longer than what I just did. Is that making any sense? So now the question is, can we do something like this with binary numbers? And the answer is, oh yeah, we can definitely do it. So here's the example of how to do it in binary. So we'll say, okay, this is a binary number as a dividend, and we'll give it another binary number here as our divisor. Same approach. So we look at this one here, and we ask, is there a 1101 in 1? Nope. 0 times 1101 is 0. 1 minus 0 is 1. Take the next digit down here, is the 0. Once again, it's 0. Then we get 1, 0, and then the 1 here, it is still a 0. And still a 0 here. Now you might say, but why do we need to do this? Well, we need to do this procedurally speaking because your divisor can be 1. If your divisor is 1, then we have a 1 right here already. So procedurally, we have to do it just like for every single digit. So we do the subtraction, we got 1, 0, 1, 1, and then we take that 0 down here. And the best thing about binary number is you either have 1 or 0 of the divisor. You don't have to do the mental math, with multiplication and kind of guesstimate how many of something you have. So in this case, we have 1, okay? So you have 1, 1, 0, 1 here. You do the binary subtraction. 0 minus 1 is 1 with a borrow. 1 minus 0 is 1, but then we have a borrow from the other one, so we get a 0 here. 1 minus 1 is a 0. 0 minus 1 is a 1, and this becomes a 0. So we take the next 0 down here. We get 1 also. So we got 1, 1, 0, 1. Okay. And once again, we have a 1, 0. And here's another 1. And I think those are all zeros. So we have 1, 0, and then 1 here, 0. 1, 0, 1, 1, 1. There's definitely just 1 down here. And we got 1, 1, 0, 1. So the remainder is going to be 0, 1, and I think that's a 0, 1. 1, 0, 1, 0 is the remainder. So you can kind of see how we can do exactly the same thing, in base 2. Whether you're using base 10 or base 2, really doesn't matter. The same method works. The next question is, how do we code this using assembly language? You can't really do this using C, by the way. That's going to be pretty hard because you have to be able to capture the digit that is being shifted out. Okay, can be done. It's just not easy. But in assembly, we actually can capture that bit that is being shifted out. So, are there any questions about the division done by hand first? Because if we don't know how to do it by hand, forget about programming it, right? Well, that's actually only partially true because that's what the neural nets are for. If you don't know how to do it, train the neural net to let the neural nets do it. If you throw in enough neurons into the neural net, it can be done. Okay, sorry, go ahead. Question?
I forgot how to do subtraction. Like the
longhand subtraction like this?
Yeah. Well, in binary at least.
Okay, it's the same method though. It's really the same method. So you basically look at this digit here from the dividend, and you say, okay, do we have any divisor in the dividend?
I get that part, but I mean the actual subtraction lower down.
The actual
like the 10110 minus 1101.
Yeah,
I forgot how to do that part.
Oh, the subtraction?
Yeah.
Oh, okay, not division, the subtraction part. Okay. So basically, I do the shorthand like this one.
Yeah.
I can use it as an example. So 0 minus 1 is 1 with a borrow. So there's a borrow here. So now it becomes 1 minus 0 minus 1, which is 0. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. So this becomes 1 minus an implicit 0 minus a 1, which is a 0 here.
Okay.
Yep. So it kind of works out the same way. It's just like, except the rules are much simpler. There are only 4 rules to remember. All right. So are we doing okay so far with the manual method, how I do it by hand? Okay, so now we want to do it using a program. So what we'll do is we'll only focus on one step, Okay, so what the one step is, whatever you have here, whatever number you have here, you compare that number to the divisor. If there's at least one divisor, you put a 1 over here in as a part of the quotient. If not, you put a 0. But whatever you do, you multiply this by whatever digit you put into the divisor so that you have this part here. Okay? And then you do the subtraction. After the subtraction, you just bring whatever the next digit of the divisor is down here. And then you repeat the whole cycle. Okay? But all this time, what you're doing is you're filling in the quotient bit by bit, starting with the most significant bit. Okay? And you're examining the dividend from the most significant bit end as well, which is actually very nice, because understanding how to do it manually like this, I'm going to open up my notepad on the side. Okay, so I think we can erase this one. I can just open a new document, that's fine. So I'm going to open it side by side like this, because I want to use assembly code to kind of implement just one step. Because one step is kind of complicated already, and I will have to copy and paste it many times. So I'm going to use a kind of lazy method to do it. Really lazy. So we'll go ahead and do it this way. So we'll do add. Okay, so we still have to remember A has the dividend. Okay, B has the divisor. So one thing that I have to change is the remainder is not going to be in register A by itself anymore. A is going to have everything shifted out for the most part. I suppose. Yeah. I cannot use register A for the remainder. So in this case, I'm going to use C as the quotient. So we'll keep this one, and then D is going to be the quote-unquote remainder. Okay, but it's not really the remainder. It is it's the number that is ongoing. In other words, D is this number. It is this number, this number, this number, and so on. Okay, so it's not really. I don't really have a name for that, because it's a number that I need in the intermediate steps of a division. So it has no specific names. Okay, so let's go ahead and specify what we're doing here. Okay, so initially I want to shift the most significant bit of A into D. In other words, I'm looking at the most significant bit of the dividend, and that's the one number that I'm comparing against the divisor to determine whether I have a 1 or 0 for that particular bit of the quotient. Is that okay? So shifting the most significant bit of A into D is kind of tricky, but it can be done. Okay. So what we do is we add D to D. So when you add, oops, sorry, I got it wrong. So we add A to A. When you add A to A, it will shift a 0 into the least significant bit, but at the same time, the most significant bit will shift into the carry. Is that making any sense? Because that's the trick that we're doing here. That is also why the instruction set has no left shift operation, because adding a register to itself is automatically a left shift. The right shift is needed because I have no other way to do right shift. Is that okay? Sort of? Okay. So that means right after this, I need a JCI instruction to capture whether there's a 1 shifted out of A, whether the most significant bit of A was a 1 before the add instruction. Is that okay? Sort of? Okay. So if it is a 1, I want to say, okay, I'm going to use a long label here. Shift 1 to D. Okay, because we're shifting a 1 into the least significant bit of D. Okay, so I'm going to make it even more clear. Least significant bit of D. Whew, that's a long name. Is that long enough? Self-documenting label. Yeah, okay. And I'll put a kind of suffix here because there's I'll need to do this multiple times. Okay, so if I'm here, it's basically saying, okay, I'm not shifting anything into D. Okay, cool. Okay, do not shift one. Okay, I'll change this to say shift 0 to least significant bit of D. Whew. Go. Is that okay? Well, that means do nothing, right? So before doing all of this stuff, I can do the pre-shifting of D up here. So all the bits that are currently in D, they're all shifted to the left-hand side by 1, so I have room for this one bit that I need to shift into it. I'm making room. Okay, so I'm commenting here, make room for new bit. Is that okay? All right. So if I don't have anything to do, because I'm shifting a 0, I'm just going to go to a merge point and basically say done with LSB least significant bit of the underscore 0, which is a suffix. Okay, we'll define that label here, done with least significant bit of D underscore 0. Goes here, and this is going to be the shift 1 to least significant bit of D underscore 0, which is what? How do we shift a single 1 into the least significant bit of D? I already made room. How about that? Okay, are we still doing okay so far with this? So the first add instruction, add DD, is making room for a new bit in D. Yep.
But that's a 0, right? So how is that? Can you explain that?
Which one?
The D is 0, right?
Initially, yes.
And then when you're adding 0 to 0, how does that make it more?
Initially, it is 0. Okay, but over time, it will have specific bits. So what I need to do, because I'm going to copy and paste this code like 7 times.
Oh, you're going to jump back to it?
I don't have a register left for counting, so I'm going to expand the loop to like 8 iterations of the same code.
Okay.
And that's why we have a suffix of 0, because the next one has a suffix of 1, 2, 3, 4, 5, 6, 7, which which looks kind of ugly. So I'm not going to do it by hand, by the way, so later on we'll see how I'm going to do this. Okay. All right, so after we do the shifting into D, okay, so that means, corresponding to this side, to the document camera, I'm shifting all the bits to one side, and I'm taking one bit from the dividend into this thing here. So the next thing I need to do is to compare what I have in D with the divisor. Okay, so I just typed in the wrong window. All right, so we need to compare. So we need to compare D against B. So, but now the question is, which one is the first operand and which one is the second operand? Which way makes more sense to me? That becomes the next question. I know I would shift a 1 into the quotient if and only if D is greater than or equal to B. Okay, which means if D is less than the divisor, less than B, I got nothing to do. Okay, just move forward. Okay, so that means it makes sense to compare D to B. Okay, and then we say JCI, if D is less than B, okay, if this number is less than the divisor, then I will shift a 0 into the quotient. So shift 0 to quotient. Okay, underscore 0. I need to suffix everything with a 0, all the labels, because that's going to change. All right, which also means if I don't perform the conditional branch, I need to shift a 1 to quotient. And this is going to be to the LSB, least significant bit of the quotient. So that means, at the beginning, over here, I'm going to add CC, make room for another new bit, but this time in the quotient itself. Okay. And this is done by incrementing C by 1. And then now we have shift 0 to quotient underscore 0, which is basically just bypassing the increment so that we are not shifting a 0. We are not shifting a 1 into it, but by default we are already shifting a 0. The shifting by 0, shifting a 0 is already done up here. Are we doing okay so far? There's one thing left to do. That one thing left to do is, if we are in fact shifting a 1, we also want to subtract divisor from D. In other words, in terms of the done by hand method, we are looking at this one here. Okay, so you can, if you look at this one, you can see how D is greater than or equal to the divisor. So once we specify a 1, okay, I think it's this one here, corresponding to this bit here, we have to subtract the divisor from D. Okay, so we can do it over here by doing a subtraction. So we have a subtraction of B from D, just like that. Whatever is left in D is fine, okay, because I'm going to use it in the next iteration. So are we doing okay so far with this code? This is dealing with one single bit position. I need to do this 8 times. So how are we going to do this 8 times? Remember what I said, well, okay, maybe I haven't said it in this class, but I say in almost every single programming class. Every time you do a copy and paste and modify, you have to ask yourself, is there a better way to do it? Yes? But we have used up all the registers already. A, B, C, and D, they're all in use. So now the question is, what are we going to do? If I need to do this 8 times, and all the registers are already in use, I can use variables. I can store something in RAM and make a loop out of it, but that's going to make it slow also. So what I'm going to do is to do an in-place expansion. In other words, I'm just copy and pasting this code 7 times. But if I do it 7 times, copy, paste, and modify 7 times, I have to change all those labels. All the _0 need to be changed to _1 for the first iteration, changed to _2 for the second iteration. And if I forget to change one of those, it will branch to the wrong place, and then the whole thing is going to break, right? So that seems pretty brittle to me. Not a good way to write a program. So how are you going to write a program to do just that? The answer is you don't. You generate it. You write another program to generate a program based on this template. Well, I mean, you guys might think it's funny. It is funny, okay? But that's exactly how templates in C++ was originally implemented. It was just an expansion of text. Okay? And that's why some of the error messages that you get in C++ when you use templates doesn't seem to make sense, because it's all done by expansion of code. All right. So what we'll do is I'm going to go back to the command line first. Okay. There's one thing I need to do to get this to work. Nope, PHP is not installed. I'm going to install it. It's easy. And you will say, why do we need PHP in this class? I'm not going to run a web server here. But remember, PHP, it can be used for any type of scripting. It doesn't have to generate an HTML document. Okay, so it's almost there. By the way, this installation won't stick, because I'm running it out of a portable version, so it's not going to stick. So we'll go ahead and we'll save this program first. So we'll go ahead and save this program into the temp folder as, let's see, how should we call this? Divide.php. Okay. And then we'll change it to become an actual PHP program. So we go to the temp folder, and then we look at divide.php, which obviously does not look like a PHP program at this point. So we change it to become a PHP program. Okay. Of course, the syntax highlighting says, hey, there's stuff here that is not recognized in PHP, like add and stuff like that. Of course, they're not recognized in PHP. This is, the assembly code of a toy processor that does not exist otherwise in outside of this class. That's okay. It's not a problem. We use a single print instruction like this to print it, right? And then you have all these zeros. Okay, so we use a loop now. So we say we can use a for loop. PHP can handle for loops. So we say I equals to 0. I is less than 8. I keep forgetting the dollar sign. I is less than 8 plus I, like that. And here's the loop. I don't really need to open and close curly braces, but it doesn't hurt to put it here. And then what we do is we look for all the underscore zeros. Replace this guy with $I. Okay. Getting a little bit lazy here. There we go.
On the JCI.
Oh, you took out the underscore too. Dang. Okay. Okay, change all the underscore 0 with underscore $I. There we go. Okay, no more copying and pasting.
Yeah, you get an extra underscore.
Extra underscore?
The very first one.
Shift 1 to O. No.
Right below the add.
Well, I got some problems here too because of the double quote.
1 to
So I have to fix the double quote too. There we go. Oh, right here. There we go. Okay, I think we are ready to go. So now we test it first, okay, and see, okay, syntax error, unexpected, close paren, expecting open bracket on line 2. Okay, let's take a look at line 2. That's line 2 right here. Oh, okay, dollar. Keep forgetting the dollar sign. It's hard to track multiple programming languages in the same semester. Cool. That seems to work, right? It made 7 copies of the same code. So now we say, okay, turn it into my divide.ttpasm text toy processor assembly language file, right? Okay. I was working on the syntax highlighting, and that's why you see that the VI can actually syntax highlight my code, because I was toying with the syntax description of this. So that's why the instructions are highlighted and the comments are highlighted as well. I'm not quite done with it, because I want to highlight the registers differently, and there's a way to do it. But I'm not gonna focus on that. So there's one more instruction I need, because the remainder is actually in D. Okay, let me switch back to the document camera here. So in the document camera, I did not actually do the subtraction down here because I ran out of room. But whatever the result is of this subtraction becomes the remainder. Okay, which is actually part of which is D. The final D is the remainder. But the homework instruction says, we want to use. Oops, I just added one. Yeah, we wanted to use register A as the remainder. So that's why I need a CPR AD. So I have to copy register D back to A in order to conform to what the assignment is asking for. Okay, there we go. So I think this one should do it. So we need to mouse pad it just so that we can copy and paste it into the assembler. So copy, Control A, select all, and then copy, and then go back to the assembler, which is here. Go to source, and make sure we start from the beginning, paste. And this is a pretty long program, lots of comments, okay, but the last instruction, as long as it's been less than 300 lines, we're good, okay, so this is the last line. We don't have any errors in column B, so looks like we are ready to go. So we go, yeah?
You're gonna put a halt in there?
Huh?
Halt.
Oh, forgot the halt instruction, thank you. So we'll put a halt instruction here, thank you. And then go to the RAM file. Okay, no syntax error. If there's a syntax error, it won't give you version 2.0 raw, which means, you know, even if you download it, it won't load into LogicSim because LogicSim checks that. So it's intentional that I would actually change this label to something else so that, you know, if you don't catch it, you know, LogicSim will catch it and go like, nope, this file is no good. All right, so we go to Files, we download as CSV. And we'll give it the name of tax divide. Go back to LogicSim. And it's okay to reset the whole thing, so I'm going to do a Control R to reset not only the registers and whatnot, but it will also reset the RAM, everything at the same time. Right click, load image, and this is tax divide. It's tax divide.csv. And this is a pretty big program by comparison, because when you look at the content, you can see it uses more than a third of the RAM locations already in this particular processor. But the advantage is it is fast, okay? Because it only performs 8 iterations of that code. Always. It doesn't matter what you're dividing by what else, it's always 8 iterations. Because it is mimicking the way we do it by hand. So when you look at the way we do it by hand over here, this method, it doesn't really matter what you're dividing by what. It will only have exactly this many steps. The numbers, the bit patterns in between will change, but the number of iterations, the number of levels you have to go would always be the same. So that means the amount of time it takes for this division to work is constant by comparison compared to the other one. Because with the other one, if you say, you know, what is 0 divided by 255, it will tell you right away, right? You know, 0 for the quotient and 0 for the remainder. Okay, it doesn't take much time. It only takes one single comparison. But if you try to divide 255 by 1, then it will go through 255 iterations of the loop. So the amount of time it takes for the successive subtraction method is variable. This one is pretty much constant. There's a little bit of variation whether we shift by 1 or not, okay, but that's not really that significant. All right, so let's go ahead and take a look at this code. So we got it loaded here. Go back to the LogicSim and do it. Oh, we have to change the registers first, give it something to do. So you guys tell me what you want it to do. What do you want it to be the dividend? Hmm? Huh?
55.
55?
255.
255, which is FF, right? Okay. And what do you want as the divisor?
DE.
Hmm?
DE, whatever that is.
DE?
Yeah.
That won't be very fun.
Oh, that'll be like 1, yeah.
It can be as low as 1. 5?
5, yeah, just 5.
Okay, 0, 5. Okay, so we put a 0, 5 here. All right, so we want to do it by hand first, just to make sure that the result is correct. 255 divided by 5, it's wholly divisible. So that will give you what?
51.
51? Okay, 51 in hexadecimal is 33. Hmm?
0 remains.
Sorry?
The remainder will
Yeah, remainder would be 0, and then quotient should be 3 in hexadecimal. Okay. And we can actually stay here and do a Control K. Now it's all done. So we have 0, 0 as the remainder and 3, 3 as the quotient. So that code does work. It just looks really ugly. Is that okay? So that trick is to use a PHP program to generate the multiple copies of the same code. Now, why, other than, it seems like a really kind of nifty trick, why is that probably a good approach? If you have to do something like this, instead of copying and pasting the code like 6 or 7 times and changing the labels, why would this be a good approach? Yeah, go ahead. Think about it. Yeah, go ahead.
I was going to say it's the same as using a declared constant for C files.
Well, it's a little bit that too, but if you think about it, if I made a mistake, okay, so let me get out of this one first. Go back to mouse pad, get out of here. Okay, so if I make a mistake, if I made a mistake in the original PHP code, I only got one place to fix. Instead of 8 individual places to fix, I only got one place to fix. Once I fix it, I run the script again. It will automatically generate the 8 instances of this, but they will be consistent. So that makes it easier to debug because I won't be introducing bugs by, oh, I forgot to update one of the instances. Especially with all the label names, and all the label names, _0, _1, if I forget to change one of those, it's going to branch to the wrong place, and the whole thing is going to fall apart. But if I do it this way, it's going to be consistent. So that's why this is a better approach than to just copy, paste, and modify by hand. Yep.
Can you explain one more time why you couldn't put this all in a loop in assembly?
Because I don't have any registers left. I have used up all the registers. So the only way to do this using a loop is to introduce variables using RAM, which is doable, but that's going to increase the lines of code is going to increase quite a bit. Because now I have to shift things, put things into the register, put it back into RAM, put something else into the register, and so on and so forth. Because we can only compare between registers, and we can only perform calculations using registers. So you will have to use a lot of swapping in and swapping out in order to get it done. So are there any other questions about this code? And this is basically the result of studying how we do it by hand. Oh, okay, I just went over that. So it's basically just doing it by hand, except we are coding it in assembly language. Is that okay? Did anyone turn in a solution like that? No one? Okay. It's okay, I did mention that, you just choose the easiest way to implement it, and that's all I'm looking for. But I do want to show you this solution because, there is a different way to do it, and it is more efficient. It's more consistent. The amount of time it takes to execute is always the same. Alrighty. So now that we get this assignment out of the way, I didn't have time to link in some additional stuff into Canvas. So let's do that now. So we go to the class. Okay, so we got 2 things to link. One is pretty easy. One is returning a single value, which is 306. The other one is how to pass parameters and how to deal with local variables, which is 307. So we'll deal with 306 first. And copy the link application. Go to modules. add one more. 307. Round meters. And local variables. Okay. So let's take a look at these two. Did we talk about calling and returning last time? I think we did. Okay. All right, so this one is kind of easy to do. It's very short. If you have a C subroutine that only does that, how do you do it in assembly? I'm returning a particular value in a C subroutine. How is it done, when you're dealing with a real C compiler, with a real architecture? So the answer is really easy. We use a particular register to store the return value. That's it. Which one? Well, depends on the architecture. If you're dealing with a 64-bit architecture of the Intel architecture, which is using the AMD 64 instruction set, it's using RAX as a register to store the return value. If you're using the 32-bit version, which is IA32, that is going to use, it's using the, no, not IA, i386, it's using register EAX for the same purpose. Using the toy processor, we're using register A for that purpose. So this is more a convention than anything else. There's nothing in the architecture that dictates and says, yes, when you're returning a value in C or C++, you have to use this register. It is simply an agreement between the subroutine being called and the caller, so that the caller knows which register to examine for the return value, and then the callee knows, okay, here's the return value. I'm going to put it into that register because I know the caller is going to look into that register for the return value. So it's basically just an agreement, a convention, but it's used by all compilers and all architectures. Is that okay? So in this case, the equivalent code in using the toy processor is going to look like this. It really is just 5, which is the label of the subroutine. This is specifying the return value. We're just putting a 5 into register A. The other 3 instructions, these 3, are the return instructions. In other words, we are loading the return address from the stack into register B. We increment D to balance the stack because now the return address is consumed from the stack. And then we perform a jump instruction to continue execution to the caller in the caller's code. Is that okay so far? Or do you guys how many people still remember what is calling and returning and how it is done in assembly language? Kind of vague, foggy.
Heavy fog. Heavy fog.
Heavy fog. Okay, so let's go back to talk about that first. So that would be this particular slide here, this note. Okay, so when you look into this one, we talked about what we do to call a subroutine, and it's done by 5 lines of code, which only consists of 4 instructions. So the first one is to decrement the stack pointer. I think we did talk about using register D as the stack pointer.
It starts at 0 decrements.
Yep, exactly. So we did talk about that. So we are allocating 1 byte on the stack, and then we load C, whatever register you choose to use other than D is fine, with a particular label. This label is labeling the returning point or the continuation point after the subroutine is done. So we put that label or the value of the label into register C, and then we store register C to the stack location that we have just allocated. So effectively what we are doing is we're saving the return address on the stack, and then we can proceed to continue execution in the subroutine. So when the subroutine has reached the end of the subroutine, it will execute these 3 instructions. So the first instruction is to go to the stack, retrieve that return address, okay? And once we retrieve that return address, we increment the stack pointer, and then after that we can use a JMP-A JMP-A is just copying register A to the program counter. In other words, register A specifies where we should go to continue execution. That turns out to be whatever return address that we push on the stack. So that's why we will continue execution over at L1 in this case. So is that okay so far with calling and returning? Is that helping you guys to remember what we talked about last week? Yes? No?
Yeah.
Okay. All right. So with that out of the way, is this part now making sense? We have a 5, subroutine called 5. It returns a value of 5, just numerical value 5, and that's all it does. Is that okay so far? More or less?
Now, I'm wondering if 5 most of the times is going to be like a variable, so you have to load it into the register that you call. Like with another variable.
It's not a variable. 5 is a constant in this case.
Oh,
So it's an immediate constant. It is a part of the instruction. So are there any questions about this particular slide? This is a really, really short module. But if there are any questions, now is a good time to ask. Going once, going twice. No questions. All right. So we are done with returning a value. Now this is a longer one. This is a much longer module because we have to talk about parameters. So before we get into the notes here, let's go take a look at some sample C code, and then you guys can tell me, what it means and how to do it. Okay, so I'm just looking at some plain C code here. So let's say this is int, and we will say add. So we have int x, int y as parameters, and inside here we say return x plus y. Okay. All right. So how do you call the subroutine? So here's main, and I'm going to say main has its own local variable. Let's call that. Let's not deal with local variables. Let's just use a global variable here, int g1 as my global variable 1. And inside here, I'm just saying g1 is add, let's say 16 and 17. All right. So looking at this C code here, this is the caller of the subroutine. This is the callee. So the question now is, how do we pass parameters? How do we let the subroutine know that its parameter x is 16 and its parameter y is 17? How do we get that information across? Yep.
use labels and allocate 6 bytes.
Okay, that's one way to do it. Okay, so what you're suggesting is we statically allocate, locations for this particular subroutine. Okay, so let's take a look at what that code might look like. Okay, so we'll do it on the side. Okay, we'll have another instance of mousepad on the side here. So what you're suggesting is, we'll have a label add x, and it has byte 0, add y, which is also byte 0, because we're just allocating, we're just reserving the space for that. And then the add subroutine will basically go to those locations, retrieve that content. So that means we have LDI A with add x, and then we use LD A indirect A to get the actual value of the variable. So this is A is the address of parameter x in this case, but once you dereference it, then A becomes just the parameter x. And then we do the same thing with the other one, y. Okay, B is the address of y, and then B indirect B, so that B is actually y in this case. And then we perform the add instruction, and that's it, right? And then the rest is really just the return code. The return code is to assume the stack pointer is pointing to the return address. So we say LDB from D, increment D, and then do a JMPB in this case to return. So these 3 lines of code is just a return code. Okay, so is that matching what you're suggesting, to use a static location so that the caller can communicate with the callee? Okay, so the caller on the other side, okay, so when you look at the main code here, if I want to call add with 16 and 17 as parameter x and parameter y, so the main program now has to perform this. It has to put 716 into A, B would be the address of addx, and then we have to do a store BA. So basically what we're doing is we're storing the value of 16 to the location at label addx using this instruction, or these 3 instructions together. Then we have something like this for 17, so we load A with 17, load B with the address of parameter y, STB A again. Then we can call the subroutine. Is that making sense? Because once we set up the parameters, then we can call the subroutine. So now we call the subroutine, which is decrement D to allocate the space for the return address. LDI, we can use register A now because it has no purpose at this point. So we're LDI A with return address 1, and we'll define return address 1 here. Then we push it on the stack, which means we're just storing that to the location pointed to by D. And then we can do a JMPI to the add subroutine. Okay, so we are looking at this code here is for setting up the parameters x and y. This code here is for actually calling the subroutine. Sorry? The return is in the subroutine itself. So if this is the entire program, we're not going to store into G1, because this is not the correct way to do it. So we'll just put a halt instruction here to mark the end of main. Okay, so this approach does work, okay, but it has a problem. It has several problems. The first problem is you cannot do recursion using this method. The reason why you cannot do recursion using this method is the recursive call, each time you call the same subroutine again, it will overwrite the parameters because you only got one set of memory locations for the parameters. So when you perform recursion, the recursive call will overwrite that location, and then you lose track of when you return. Now calling and returning is fine. It's just that we have lost track of the parameters. Because the calling and the returning will still be using the stack to store the return address, but the parameters won't be there anymore. So when you implement, let's say factorial using this way, you lose track of the parameter, which is what you need in order to do that multiplication that you need before you return. So this is not going to work with recursion. Okay, big deal. Only certain people like Professor Fox likes, recursion, right? And you go like, well, and also we know everything that is recursive can be done non-recursively. You just have to maintain your own stack as a data structure. Okay, so maybe recursion is not a very good reason not to use this approach. There are 2 more reasons why we should not use this approach. The first one is it is wasteful. Wasteful, what do you mean by wasteful? So what do you think would be the number of subroutines in any reasonable program? Yeah, just a ballpark number. Let's call it 300, okay, which I think is not too unreasonable. Okay, so let's say a program has 300 subroutines. Okay, we don't know exactly how they nest, which one calls which one, and so on, but 300. Out of the 300 subroutines, how many do you think will be active at the same time? Active at the same time means main calls A calls B, B calls C, then main A, B, and C are all active at the same time. So it's basically asking how deep can you go when you're dealing with a normal program without recursion. 20 levels. Let's make it 30 levels. Okay, so let's say we have 300 subroutines, but we only go 30 levels deep at any particular time at the most. Well, what happened to the other 270 subroutines and the area that you have reserved for the parameters? It's all wasted, right? Because they're just sitting there doing nothing because those subroutines are not being called. So that's what I meant when I said it is wasteful. Okay. But then you say, but we got lots of RAM now. Being wasteful a little bit is not a big deal. Okay, we got 16 gigs of RAM, and my gaming PC has got 32 gigs of RAM. It's not a big deal. Okay, but that's one last reason why this is not a good idea. Multi-threading. Okay, multi-threading is not a particular topic, that is specific to this class, but it is important. So can you guys tell me what is multi-threading? It's a single program, single process, but it has multiple threads. Why do we write programs like that? Where there's only it's a single program, but it has got multiple threads.
So the processor can perform more than one calculation at a time?
So the processor can perform more calculations than one at the same time. That's one reason. And then the second reason is logically, there may be multiple things you're performing that are logically in its own thread, especially with GUI programs. Graphical user interface programs, like games for the most part, they're multi-threaded, by its very nature. So if you do not program in a multi-threaded way, it is very difficult to make things appear to be happening in parallel. It can happen, you can do it, but it's very, very difficult. It's much more natural when you say, oh, you know what, these two functions or these 5 functions, they can all be executing at the same time. Okay, that's a very simple concept, right? You have 5 functions and they can all be running at the same time. They can then call their own subroutine at the same time too. Is that okay? In the good old days, people would argue and say, well, that doesn't make sense because you only have one single core, you only have one single CPU. By pretending that you have multiple processors and by pretending that you can multi-thread, really it's not going to be any more efficient than not having a program that is programmed in a way that is multi-threaded. But these days, how many cores do you have on the typical desktop computer? 4 at least, right? I mean, if you look at the latest generation of the i7, they have what, 6, 8 cores? Okay, and each core has hyper-threading, so that so each core has a virtual core. So when you have 8 real cores, you have 16. You can have 16 threads executing at at exactly the same time. What does that have anything to do with this program?
Well,
You'd be allocating.
yeah, you'd be allocating all of that to all of those threads, wouldn't you?
Well, what if those threads decide to call the same subroutine at the same time?
And they'd all try and be loading off the same.
They'll be clobbering each other, right?
Yeah.
Because you only got one space to put everything. So let me go back here. Okay. So what we are talking about is we have thread 1. This T1 is one thread.
Lower.
And then T2 is another thread. Okay. So T1 is happily doing its own thing, that has no interference with T2. And then T1 decides to execute at one point and execute a particular subroutine. Let's say our add subroutine here. So T1 is calling add, and then T2 at some point, while T1 is still in add, T2 decides I'm going to call add 2. So now we have 2 instances of add, happening at the same time. Right at this moment here, this call is going to clobber the partial result or whatever partial result is being done in this particular case, because they share the same space for the parameters. So that's not a good thing. Now, can each instance return to the right place? Yes, that is not a problem, because T1 has its own stack, T2 has its own stack as well. So we are dealing with 2 different stacks in this case. So as a result, calling and returning is not a problem. Keeping track of the parameters is a problem. Okay. So this particular problem is called reentrancy. For those of you who might get into systems programming, the term is reentrancy. So reentrancy is an issue that is directly linked to having a static place for storing parameters. Okay, so we got 3 reasons to not use a static locations to store your parameters. Where else can we put the parameters? Hmm? RAM. But which part of RAM? Because static locations are in RAM too.
Stack.
The stack. Okay, so we gotta use the stack to store our parameters. So now, when we switch back to the notes, which is 306, there we go. Nope, 307. 307 is the one that talks about the stack. I can always get it from here. Okay, so now we are looking at a subtraction code. Okay, this is the subtraction subroutine. So let's focus on the C code first. This is a subtraction subroutine, which is about the same as our add subroutine, except this one does subtraction instead of adding. So what we do is we are going to push the parameters on the stack. In this case, we're pushing 5 first. So 5 would end up with a higher address than a 3. This, from the caller perspective, is translated to this code in assembly. So we'll go ahead and take a look at the assembly code line by line to see why it is doing the same trick as the C code. Okay. Line 1 is just initializing register A with a 5. Okay, no big deal. Line 2 is allocating a byte from the stack. Remember, the stack grows down, which means the more items you push on the stack, the lower the stack pointer. So we do a decrement D on line 2 to allocate 1 byte on the stack, and then we just store whatever A has on the stack. So now the stack has a 5 on it. Is that okay? Then we do exactly the same thing to the 3. So we push the 5 on the stack, then we push the 3 on the stack. The 5 has a higher address than the 3, because whatever you push earlier is going to have a higher address than whatever you push later. From line 7 to line 10 is the call sequence. Okay, we are storing the return address into a particular register, allocate a byte on the stack, and then we store the return address on the stack. Then we continue execution in the subroutine. That's just regular call. Is that okay? But what you need to do is to keep in your mind what the stack has at this point. At the stack pointer, it has got the return address. 1 byte above the stack pointer, the return address, is the 3, which is your first parameter, and then 1 byte on top of that is the 5, which is your second parameter. Is that okay? Is that making are you making a map in your mind about what is on the stack? Okay. So at this point, we are continuing execution in the subroutine. So now the question is, what is the subroutine going to do to get back to parameter X and parameter Y? So for that code, we're going down here. So the JMPI to subtract is going to continue execution at the label subtract. So the first thing we do on line 2 is to say, okay, we don't want to mess around with register D, because the stack pointer is one thing that you don't want to mess around. You want to make sure that you keep it balanced and not do anything, not change it unnecessarily. So what we do is we make a copy of register D, which is the stack pointer, to register C. Okay, so register C is just a copy. We load, okay, this is just increment. Okay, so we're incrementing C by 1. Now, when you're at this instruction, C is pointing to what? C is the same as the stack pointer, and they point to what thing on the stack? The return address. Okay, so they both point to the return address. But when you add 1 to C, it points to the thing that is above the return address, which is 3, your first parameter. But it is the address. Okay, so C has the address of parameter X. That's why you need to load indirect. Then A becomes the actual parameter X, the value of the parameter. Is that okay? If I add 1 more to C, if I increment C 1 more time, then it's going to have the second parameter, the address to the second parameter. That's why we need to use a load indirect so that B becomes the second parameter. So A is now the first parameter, B is the second parameter. We just do a subtraction. Now the subtraction automatically makes the result stored in A, which is what we want, because the return value is supposed to be stored in register A. So that's done. And then the rest of the code is the typical return, sequence, which is to use the stack pointer to store, to retrieve the return address and put it into register B. We increment D because we want to deallocate a byte that is now useless, okay? Because we have retrieved that byte already, and then we jump to whatever B is pointing to, which is the return address. So at this point, on line 14 of the callee, of subtract, we continue execution back in the caller at the label of return address. So at this point, we got two little things to do. We have two increment D instructions here because we have to deallocate those 2 bytes. One is used to store 3, the other one is used to store the 5. Because those parameters are of no use anymore at this point. The subroutine is done. Okay, why do you want to keep the parameters on the stack when the subroutine is already done? Yep.
What I noticed is that you increment D before you make the return, before you jump to B, and that's what I was worried. I was thinking, where is the last increment?
You mean here?
Yeah.
It's deallocating the return address areas.
Yeah, this is the callee or the subroutine deallocating the byte that we use to store the return address. Because the moment you retrieve it and put it into register B, we don't need it on the stack anymore. We have just retrieved it, right? So that's why you increment the stack pointer to basically say, okay, this location is no longer useful to me anymore, and as a result, we deallocate it, and then we jump to whatever register B is pointing to, because what we retrieve from the stack should be the return address.
Makes sense.
Is that okay?
Yeah. Could you also do before you allocate, before you store that into B, could you jump D and then increment 3 times?
Once you jump, you cannot continue execution anymore, right? The jump instruction is immediately effective, which means once you do a JMP whatever, you continue execution at whatever.
Yeah.
So whatever instruction is right next to after the JMP instruction is of no consequence anymore. So the ordering of these 3 instructions cannot be changed. It absolutely needs to happen in this particular order. Because if you increment first, then you're not retrieving the return address anymore, because the return address is pointed to by register D at this moment. So you have to retrieve it first. But you cannot change the order of JMP versus the increment either, because if you change the order, then you will have continued execution in the caller's code, and you would not have a chance to increment D anymore. So that's why these 3 instructions, you cannot change the order at all. They are basically locked. So we still do okay so far with the use of the stack in assembly code. Now the toy processor, is kind of a toy, okay, because it only has 256 locations. But the approach of doing things, the way that we store parameters on the stack, the way that we store the return address on the stack, the way we utilize those locations in the subroutine, it is used in every known architecture that I know of. Okay, any compiler, any architecture will crank out code to the same effect. So one last question. We got 2 minutes left. So zooming out, why is this important? Other than from an academic perspective, why is this important? Why do we want to understand how a C compiler cranks out code? Any idea? Okay, so I'm going to go to a particular page. Okay, this is my little real-time kernel that I wrote a long time ago, which basically means if I read the source code, it will take me like 2 or 3 days to get used to it again, even with a lot of comments. But this is a little real-time kernel. Basically, it supports multi-threading. It supports round robin, time slicing, and all those useful feature of a real-time kernel. It doesn't have a file system. It is not fancy, but it does perform multi-threading fairly well because I use it in some of my other programs that I do. But the interesting part is it is written entirely in assembly language. So if you look up the name AVR, as an architecture, it's a very simple 8-bit architecture, not really unlike the toy processor. It's a little bit more, has more instructions than the toy processor, has a lot of convenience features, but it's about the same. The real-time kernel itself is written 100% in assembly, but it has a C interface. In other words, the API to that whole thing has regular structures in C. You can call all of these subroutines from a C program. So you can write a program in C, compile the program using GCC, crank up whatever C code that's coming out of it, and then link it with the real-time kernel, which is written entirely in assembly, and it will work. So now the question is, how does it work? Because RTK initialize is called from the C code, but the actual implementation is entirely in assembly. So how does it work? It's what we just talked about. In my assembly code, I have to understand that Q as a parameter, as a pointer, is pushed first on the stack, T is pushed second on the stack, and then the return address is pushed third on the stack. So when I look at the stack pointer, I know where to go to find the two parameters. Is that making any sense? This one does not return a value. Some of these return values. So for the ones that do return values, such as this one, okay? So this one returns an integer. So my code needs to understand, okay, so I can do all the calculations, but how am I going to communicate back to the caller? This is the return value. Well, I have to know which register is responsible for storing the return value. So, which is exactly what we just talked about in this class, okay? It's not register A, because they name the registers differently, but it's the same idea. They have dedicated registers just to store the return value. So as the callee, when I wrote these programs in assembly, I have to remember, okay, this is how we pass parameters, this is how we specify the return value, so that my assembly code can interface with the C callers, or the code that is done in C. So one more question, because I know the next class, usually Mr. Fox is not here this early. Next question, why do I write this entire real-time kernel in assembly without a single line of C? There are two reasons. It's efficient, okay? Well, assembly code is efficient, but modern compilers are surprisingly efficient as well. Okay, but that's one reason.
Would it be able to run on anything compared to like C would have to be compiled for a certain
Okay, I think you hit the nail. The things that I need to perform in the real-time kernel cannot be specified in C. Because I have to say, okay, save all the registers into this chunk of RAM. There's no such thing in C to do it, okay? But there's one more reason. Well, the compactness is the reason, okay? So what you mentioned is true. The entire real-time kernel, is, can anyone guess the size of this real-time kernel? Just order of magnitude.
file size or?
Just in terms of number of bytes. Huh? Few megabytes?
Kilobytes.
Huh? Kilobytes. Okay, how many kilobytes?
150.
2. 2 kilobytes, 2.5-ish, kilobytes, depending on what feature you enable. So the whole thing is only 2.5 kilobytes because it has to live on devices that only has 8 kilobytes of code space. It cannot be that big. It has to be like pretty small and compact. But would this be something that you might need to do in the future? maybe, maybe not, okay? Depending on whether you want to kind of get into robotics and, automation and stuff like that. If you're getting into those things, you might need to do something like this because you will be working with a platform that has no known operating system to work on. So you have to write everything. You have to write your own kernel. You have to write your own file system and so on. All right. Well, we are running out of time today. There's no homework assignment at this point because we have not covered enough topics. I will still be over at the lab, so that if you guys want to kind of go over what we talked about today, I'm more than happy to explain all of that stuff.